In our last unit on heat, we talked about changing something from a solid to a liquid. And we said that in order to get something to change, we had to go from this nice orderly type of substance to get the heat enough, energy enough, to begin to break the intermolecular forces between them so that they would start to move more. And the temperature wouldn't change until it all became liquid, and then at that point we would heat it up until we reached the point at which vaporization could occur, and the substance begins to become a gas. Again, temperature not changing, but energy continuing to go in to pull those particles further apart. Once they're all completely apart, then it can become gas and the temperature can go up again. So we're going to talk about that gas pressure today. All right, if you have a liquid, for instance, a bottle of pop. At the top of the bottle of pop, you have a layer of air that's compressed. And you've all opened the can, and if I open this one, it's been sitting here open, so it's not going to make that psst sound, but you've all heard the psst sound when you open a can of pop or a bottle of pop. That is the sound of freshness. When you open, when they bottle the soda, you know that what gives the soda the bubbles is the carbon dioxide. If you've been to Quick Trip and you've watched or anywhere that you can make your own fountain drinks, and you watch it, sometimes it'll look like it's coming out in stripes, and you'll have a dark stripe and a light stripe. That light stripe has the carbon dioxide, is carbonated water, carbon dioxide dissolved in water. And then the dark stripe is the syrup and the sugar and the coloring. And that, of course, mixes together to make your drink. You've all had a drink where it's gone flat, and it loses that taste, the bubbliness. You've had a drink where it was all bubbles and no sweetness, and it's very bitter tasting. Okay? So they actually store it under pressure. They add a little bit of extra pressure in there so that that carbon dioxide gas doesn't come out of the liquid as time goes on. Well, eventually it will, but that's why you have due dates on things. So when you open this, you release some of that pressure, and you'll notice the bubbles begin to rise to the top, and that is that gas escaping. It's not changing phase. It's always been a gas. It was just dissolved, and now it's escaping from the dissolved state. Okay? But it's similar to what we're talking about with heat and temperature, because this is pressurized. But the same thing happens if you have a bottle of water, just a bottle of water, and it's in a heated car. That water vapor, that water inside, energy is going to make it start to want to become a gas. And the particles will go back and forth, and then once you open it, they can escape, and then, of course, evaporation occurs. Okay? But if you've got it in a closed container, you have a pressure from that water vapor that's up here in the top. Okay? Why is this important? Well, stop and think about a gas. How are you going to collect a gas? You can't just take an empty bottle and have a reaction going where the gas is just going to go in here, because what's in this bottle right now? We've got air. So we have to collect the gas in a way that we won't have any air, and we collect it under water. Here is a lovely picture. This is gas generator. What that means is that there is a reaction going on, and in that reaction, a gas is being formed, and this is a water, what you would call a trough or a bucket. And there's a beaker that's turned upside down in there that's completely full of water. And as the gas bubbles, it's going to replace that water. So you can see here, now we have all that gas that's been produced. But the question is, let's say that this was vinegar plus baking soda, which we all know makes carbon dioxide gas plus other stuff. All right. So, is this pure carbon dioxide in here, if that was the reaction going on? And the answer is no. Because there is also water vapor in there. The warmer it is, the more water vapor is going to be in there. So we have to not only figure out the pressure of the gas inside the container, but we have to subtract the pressure of that gas from the water. This is what we call Dalton's law of partial pressure. I don't know if that's labeled in here. Yeah, here it is. Dalton's law of partial pressure. The total pressure is related or is equal to the partial pressures of each of the gases in a system. And so if you are a scuba diver, they mix different quantities in your scuba tanks, and I don't pretend to know what I'm talking about because I've only ever snorkeled. But they'll have different, I think they put some helium in there, I think, or argon maybe, along with your nitrogen and oxygen. And they may put extra oxygen in there. And depending on how deep you're going to go, it's going to depend. Well, you could figure out the pressures of each of these. And you have a worksheet. I'm on the wrong page. You have a worksheet within your packet called Dalton's Law of Partial Pressure. Okay? So this is what I'm attempting to explain here. For instance, in this question below the information there, it says a container of gas that has a pressure of 450 kilopascals. Kilopascals are a valid measurement of pressure. We don't use it. We tend to use atmospheres. The purpose of doing all this is because you would then do a lab, and I'm actually going to go through the lab with you. I'm going to see if I can get into school tomorrow to get the materials to do the lab for you. But you would have a lab where you would be taking hydrochloric acid and magnesium and producing hydrogen gas and collecting that. Well, we would also need to know the pressure of the water. So we have to understand this concept. So if this is our total pressure in kPa, oh, and the reason I'm telling you this is because the document you have in here that should have been next, but apparently wasn't. Oh, here we go. This document, the partial pressures are in millimeters of mercury, or in torr, because that's one and the same. So we're not going to necessarily use atmospheres here. That was my point. All right, so here is our question. We have a total pressure, and we have three gases. We have the pressure of hydrogen, which is there, the pressure of oxygen, which is there, and it wants to know the pressure of nitrogen. So you just add them up. 450 equals 210 plus 125 plus pressure of nitrogen, and then solve for nitrogen. Okay? It's pretty simple. So if we're talking about a gas, when we talk about Dalton's law of partial pressures, it tells us we have helium gas that we're collecting over water at 28. Well, that makes a difference, the temperature, because the warmer it is, the higher the pressure is going to be. What is the partial pressure of the helium, given that the barometric pressure, that's going to be our total pressure, is 750? Well, here's our lovely little chart. What did we say it was? I've already forgotten, 28 degrees Celsius. So if the temperature is 28 degrees Celsius, the pressure of that water is going to be 28.349. So the pressure of the water, so total pressure is going to be equal to the pressure of the water plus the pressure of the helium. We know that the total pressure is 750 millimeters of mercury. The pressure of the water, I've already forgotten, 28.349. So what would the helium be? And if I get my handy dandy calculator out, I get 721 millimeters of mercury. All right. The next one, three of the primary components of air are carbon dioxide, nitrogen, and oxygen. At 1 atmosphere, so 1 atmosphere is our total pressure. The partial pressure of carbon dioxide is 0.27 atm. Nitrogen is 0.53 atm. What is the partial pressure of oxygen? So, solve for x. 1 minus 0.27 minus 0.53, 0.20 atm. The third one, a sample of gas is collected over water at a temperature of 35 degrees. The barometric pressure reading is 1.1 atm. This is our total pressure. So we need pressure of water plus the pressure of the gas. So we have to look it up. Now, here's our next problem. What measurement are we using? We're given atmospheres. What measurement is in the table? Millimeters of mercury. So you have to pick one. You can either change millimeters of mercury to atmospheres, or you can change atmospheres to millimeters of mercury. Let's first look up what at 35 degrees, what is our pressure? 35 degrees, it's 41.175. All right, I'm going to go ahead and change to atmospheres because I like it better. So I'm going to take 41.175 millimeters of mercury. If you look back at the beginning, you will remember that 1 atmosphere is equal to 760 millimeters of mercury. So I'm going to take 41.175 divided by 760, and I'm going to get 0.054 atm. So that's going to fit in here now. Now I just subtract that from 1.1, and the pressure of the gas is 1.05 atm. Okay? Pretty simple partial pressures. Like I said, I'm going to try and get this lab, either find it online to share with you or make it up my own, or actually do it, depending on what the situation is. So, yay.